On the evening of July the 28th, 2026, while most of the world's attention was locked on the earthquake unfolding in Japan, the ground moved again beneath a fault in Northern California that almost nobody outside working seismology has ever heard of. At 7:40 p.m. Pacific Time, a magnitude 4.3 earthquake struck 5 miles southeast of Cloverdale, California. The United States Geological Survey didn't classify it as an isolated event. Within hours, their own product feed flagged it as the potential mainshock of an earthquake sequence, logging more than 160 associated seismic events in that same window. That word, potential, carries the entire weight of the uncertainty in this story. This fault runs directly toward the Bay Area, and its buried geological record holds earthquakes considerably larger than anything in its modern catalog. The Cloverdale earthquake itself caused no injuries and no structural damage. USGS's automated impact assessment system issued a green alert, the lowest category on the scale, for both fatalities and economic loss. More than 520 people submitted felt reports, ranging from towns close to the epicenter like Healdsburg and Geyserville out to San Francisco, more than 100 kilometers away. The strongest recorded shaking reached intensity 5 on the modified Mercalli scale, enough to rattle dishes and knock pictures crooked, nowhere close to structural damage. On an ordinary week, a magnitude 4.3 in Northern California is a minor local news item. This one is different for reasons that have nothing to do with how hard it shook. The first reason is the sequence size itself. Aftershock productivity scales with the size of the main event, and the statistically expected population following a magnitude 4.3 earthquake is a small handful of events, perhaps a dozen, decaying quickly. A sequence population in the hundreds is a fundamentally different signal. It indicates high productivity, and high productivity means something specific about the underlying rock. When a single locked patch on a fault fails cleanly and settles, you get a small aftershock population. When a broader volume of crust is sitting close to failure and one piece releases, the resulting stress redistribution activates everything around it. That's what a sequence of more than 160 events looks like. Not one patch breaking, but a section of crust actively reorganizing itself. USGS's own forecast product for this sequence specifically expects at least one additional aftershock of magnitude 3 or greater within the week, following the initial rupture. The second reason involves exactly which fault this is. The Cloverdale epicenter sits on the Maacama fault system, a right lateral strike-slip fault running northwest to southeast through the northern California coast ranges east of the more famous San Andreas. It dips somewhere between 50 and 70 degrees to the east and carries a substantial share of the tectonic motion between the Pacific and North American plates in this part of the state, motion that the San Andreas alone doesn't fully absorb. According to the deformation model built for the 2023 National Seismic Hazard Model, the Maacama's slip rate runs at roughly 9 millimeters per year. For comparison, the San Andreas offshore of this same region runs at roughly 24 millimeters a year, the highest rate on the local map, and yet has produced almost no cataloged earthquakes along that particular section. A reminder that a fault's slip rate and its earthquake history don't always move in lockstep. The Maacama also creeps, meaning the ground on either side of the fault slides past itself slowly and continuously without producing an earthquake at all. That creep rate runs somewhere between 2 and 6 millimeters per year, visible in the built environment where curbs and infrastructure crossing the fault trace have been measurably offset sideways over time. Creep is often described publicly as a pressure release valve, and that framing is incomplete in an important way. Researchers who've studied this fault's recent behavior have stated directly that while creep does bleed off some potential seismic energy, seismic strain is still accumulating along this fault, strain that can be expected to eventually release in earthquakes. Running the arithmetic, if the fault moves 9 millimeters a year total, and creep accounts for somewhere between 2 and 6 of those millimeters, then somewhere between 3 and 7 millimeters a year is not being released aseismically. That residual accumulates as elastic strain in the surrounding rock. It doesn't disappear, it waits. The third reason this earthquake matters is that it wasn't the first recent event on this exact system. On the morning of June 24, 2026, a magnitude 5.6 earthquake struck near Ukiah in Mendocino County, its epicenter directly beneath a Buddhist monastery in a sparsely populated stretch of mountainous forest. It was the largest earthquake in that region in nearly 9 decades, and more significantly, the largest earthquake ever attributed to the Maacama fault in the survey's entire instrumental catalog. Shaking was severe close to the rupture, with seismometers within 10 kilometers recording intensities between 6 and 8, and USGS's impact model estimated roughly 10,000 people experienced intensity 7 shaking. More than 4,200 felt reports were filed. Thousands of Mendocino County residents lost power, and there was minor damage along with some injuries. The focal mechanism matched the Maacama fault's known geometry exactly. So here's where that leaves the timeline. The Maacama Fault produced the largest earthquake ever recorded on it on June 24th. 34 days later, it produced a magnitude 4.3 with a sequence of more than 160 events, roughly 55 kilometers to the south-southeast along the same structural trend. 2 notable earthquakes 5 weeks apart, on a fault that had never before produced a catalogued event above magnitude 5.6 in the entire instrumental record. This doesn't mean a large earthquake is coming. The instrumental catalog for this fault is genuinely short, and short catalogs can generate apparent pattern shifts that turn out to be artifacts of limited sampling rather than a real change in the fault's underlying behavior. What it does mean is that a fault the public has essentially never heard of has now twice demonstrated it's doing something worth paying attention to. The June 24th earthquake also taught a separate, uncomfortable lesson about earthquake early warning technology. Shake Alert, the West Coast's earthquake early warning system, the most advanced public system of its kind in the Western Hemisphere, detected the Ukiah rupture and issued an alert. Roughly 657,000 warnings went out through the MyShake app. But people in the zone of strongest shaking received their alert after the strongest shaking had already reached them. The first Shake Alert message went out 5.5 seconds after the earthquake began, and in that time, seismic energy had already traveled outward roughly 18 kilometers. Everyone inside that radius was already experiencing shaking when the alert generated. Researchers who have documented this pattern describe the conclusion plainly. These systems are detectors, not predictors, and they will never provide timely warning to areas directly above the rupture. That's not a flaw in Shake Alert, it's a description of basic physics. An earthquake has to begin before anything can detect that it's begun. The warning travels at the speed of light, while the damaging seismic waves travel at a few kilometers per second. The further you are from the rupture, the more warning you actually receive, which means 30 seconds of warning in San Francisco for a distant quake is genuinely valuable, while directly above the fault itself. The math simply cannot be beaten. Here's a genuinely interesting scientific detail that surfaced while researchers were examining the seismicity around the June rupture. There's a distinct linear band of earthquakes visible in the catalog between the Maacama and the neighboring Bartlett Springs faults, the clear signature of an active geological structure. But it doesn't appear as a mapped fault trace in the National Quaternary Fault and Fold database, the authoritative United States inventory of faults considered currently active. California Geological survey mapping shows structures in that general area, but classifies them as pre-quaternary, meaning not currently active. Working seismologists publicly asked for help identifying this feature and were pointed toward a 2013 paper in the journal Geology that appears to describe the same structure. There's a seismically active zone in the Northern California coast ranges that isn't fully accounted for in the National Active Fault Database. Not hidden or suppressed, the earthquakes themselves sit right there in the public catalog, simply not yet formally assigned to a named map structure. If you want to understand why researchers are watching this specific sequence so closely, rather than treating it as routine, that ambiguity about the Maacama's own history is a big part of it. A subscribe genuinely helps more people see this kind of detailed breakdown, and this is exactly the sort of slow-developing regional story worth tracking closely over the coming days. The Maacama's documented history runs considerably longer than its short instrumental catalog suggests. Careful excavation of sediments near the town of Willits identified fault offsets pointing to several large earthquakes on this fault within roughly the last 100-200 years. That study deliberately assigned no specific magnitudes to those ancient ruptures, since converting a single location's offset measurement into a precise magnitude isn't defensible science. But researchers reviewing that record, explicitly flagging their estimate as informal, put the likely size at magnitude 6.5 to 7 or larger, reasoning that smaller earthquakes generally don't leave a preserved geological record at all. Applying the logarithmic energy scale, where each whole magnitude step represents roughly 30 times more energy, a magnitude 6.6 releases approximately 30 times the energy of June's magnitude 5.6 event. A fault that creeps and still produces ruptures of that size in the preserved sediment record is a fault where creep alone clearly isn't sufficient to prevent significant earthquakes. Following this fault system southeast from the current activity connects it directly to a structure with serious implications for one of the most densely populated parts of Northern California. The Hayward-Rodgers Creek fault begins in the general area of this sequence and runs southeast through Santa Rosa toward the Bay Area. For decades, there was an open scientific question about what happened to this fault where it reached San Pablo Bay. In 2016, subsurface imaging led by USGS researchers and published in the journal Science Advances answered it definitively. The Hayward and Rodgers Creek faults are directly connected beneath the bay, with the Hayward fault bending roughly 10 degrees to the right as it crosses. They function as one continuous structure, with a combined length of roughly 190 kilometers. The maximum modeled magnitude for a rupture along that full combined length reaches 7.4, though USGS is explicit that multi-fault ruptures of this kind are real but considerably rarer than single-fault ruptures, meaning that joint 7.4 scenario is less likely than the individual Hayward fault scenarios alone, which model at magnitude 6.8 and 7.0, already among the most consequential earthquake scenarios in the entire United States, given that the Hayward fault runs directly beneath the East Bay's population centers. To be completely clear about what is and isn't being claimed here, a magnitude 4.3 near Cloverdale does not load the Hayward fault. There's no physical mechanism by which it directly does. The connection between these events is structural, not causal. The sequence is unfolding on the northern end of a continuous fault system that runs into the most densely populated corridor in Northern California, on a segment whose preserved paleoseismic record runs 2 full magnitude units larger than anything in its modern instrumental catalog. One important distinction worth clearing up involves a separate cluster of earthquakes appearing in the same general map view near Clear Lake and the Geysers, the largest electricity-producing geothermal field in the world. That's a genuinely different phenomenon. Steam withdrawal and fluid injection at geothermal operations remove mass and heat, causing reservoir rock to contract, and that contraction produces small induced earthquakes. This induced seismicity is real and openly documented, but it stays confined to the reservoir volume itself, shallow, small, and spatially bounded. The Cloverdale sequence sits on the Maacama structure specifically, more than 55 kilometers from the geysers, an entirely separate process occupying the same general map view. It's worth understanding the actual statistics behind why USGS uses that specific word, potential, when classifying an earthquake like this one as a possible mainshock. There is no physical property that distinguishes a foreshock from a mainshock at the moment either one occurs. That classification is only ever available in hindsight, after a larger event either does or doesn't follow. The established base rates are genuinely reassuring, up to a point. Following any given earthquake, a larger event follows, within 3 days, roughly 6% of the time, and within a week, roughly 5% of the time, meaning about 19 times out of 20, nothing larger comes, and a magnitude 4.3 like this one is statistically about 95% likely to remain the largest event of its own sequence. The reason to pay attention isn't that a larger earthquake probably is coming, it almost certainly isn't. It's that the roughly 5% case cannot be reliably identified in advance by anyone, with any instrument currently available. That's not a hypothetical caveat. It's a documented historical pattern. In April 2016, a magnitude 6.5 earthquake struck the Futagawa and Hinagu fault zones beneath Kumamoto, Japan, and was treated at the time as the main event, with emergency response mobilizing and residents returning to damaged buildings. 28 hours later, a magnitude 7.3 struck the same fault system. The first earthquake was only reclassified as a foreshock after the second, larger one arrived. Japan's own seismic agency has since built that lesson directly into its post-earthquake guidance, which is exactly why, following this week's magnitude 7.1 earthquake in Kumamoto, officials there warned residents that comparable aftershocks remain possible for roughly a week, a protocol that exists specifically because of what this same fault system did in 2016. So here's where this leaves things for Northern California. A fault most residents have never heard of has now produced its 2 most significant recorded earthquakes within 5 weeks of each other. A June 24th magnitude 5.6 near Ukiah, the largest ever attributed to the Maacama fault, followed by this week's magnitude 4.3 near Cloverdale, carrying an unusually large aftershock sequence of more than 160 events. Neither event caused significant damage. Neither one guarantees anything about what comes next. But the fault's own preserved geological record holds evidence of earthquakes considerably larger than either of these, and it connects structurally, if not causally, to a fault system running directly beneath one of the most densely populated regions in Northern California. What actually matters going forward isn't any single future magnitude number, it's the shape of the aftershock distribution over the coming days. If aftershocks stay tightly clustered around the current rupture zone, that's consistent with a normal sequence gradually decaying and releasing local stress. If instead they begin elongating along the fault trend, either northwest toward Ukiah and June's rupture zone, or southeast toward the Rodgers Creek fault, that would indicate stress actively transferring onto adjacent fault segments, and that kind of segment-to-segment progression is exactly the mechanism by which a moderate earthquake sequence can evolve into something larger. USGS's own forecast for this sequence provides a concrete, checkable benchmark, at least one magnitude 3 or greater event within the week following Tuesday's rupture. Where any future event in this sequence lands matters considerably more than simply whether it happens at all. One question worth addressing directly, given the timing, is whether this week's earthquake in Japan and the sequence in California are actually connected. They aren't, and the reasons why are genuinely more interesting than a simple yes would have been. Earthquake triggering across long distances works through two distinct mechanisms. Static triggering involves a permanent stress change in the crust immediately surrounding a rupture, powerful but falling off so rapidly with distance that it's effectively confined to within one or two rupture lengths, meaning a rupture spanning a few tens of kilometers cannot meaningfully load a fault located thousands of kilometers away. Dynamic triggering works differently through the passing seismic waves themselves, and this mechanism genuinely can operate at global distances. It was documented most notably following the 1992 Landers earthquake in California, which produced measurable remote seismicity increases in locations as far away as Yellowstone. But dynamic triggering has a consistent signature. It shows up strongest in geothermal and volcanic areas containing pressurized fluids, and it typically appears during or within minutes to hours of the seismic waves actually passing through a region, not roughly 12 hours later, on a strike-slip crustal fault far outside any geothermal reservoir. The defensible conclusion is that these events are independent of one another, each representing strain accumulated locally on its own fault system, released on its own schedule. That independence is actually the less comforting version of this story, in a sense. If California's activity isn't connected to Japan's, it means the Maacama fault moved purely on its own accumulated strain, at its own roughly 9 mm per year rate, producing its largest recorded earthquake 5 weeks before producing this unusually large aftershock sequence, entirely independent of anything happening on the other side of the Pacific. The West Coast reading is a local reading. It tells us about the current state of the Maacama fault zone specifically, and nothing whatsoever about what's happening beneath Kyushu. We'll be tracking this aftershock sequence closely over the coming days as the picture fills in. Thank you for watching, and I'll see you in the next one.